it's a real pleasure to introduce Professor Ahmed Elbanna, my colleague and friend, at UIUC. And I just want to say a few words about his academic trajectory. He hails from Egypt, where he holds a BS degree in civil engineering and MSc degree in structural engineering from Cairo University. And then he moved to the US to start graduate studies at Caltech, where he holds a degree in a MS degree in applied mechanics and a PhD in civil engineering that he earned in 2011. So after a short stint, about 2 year stint in the Department of Physics at the University of California, Santa Barbara, he started his faculty career at UIUC in 2013, if I'm correct, as an assistant professor, and he was promoted to associate professor about 2 years ago. Ahmed has a very interesting research agenda. His research is at the intersection of solid mechanics, material science, geophysics, geomechanics, and it's with application as diverse as the mechanics of earthquake, as we're going to learn today, or the design of nature-inspired materials. And in particular, I want to quote a paper that he worked with one of his PhD students about the strong adhesion of muscles on surface. And I was interested in that one because coming from Belgium, and muscles are our national dish,
Okay, great.
But anyway, so the study was on understanding of the mechanism and what we can learn from that to develop new ways to toughen interfaces. Okay, so he has received several awards. I just want to mention the one on the NSF career proposal that he got a few years ago. So, please, Ahmed, the floor is yours, and I'm really happy to welcome you again in a virtual setting, but I mean, still a pleasure to hear from you.
Thank you very much, Emmanuel, for the very kind introduction and the invitation. As I mentioned, I had very fond memories from my last visit in 2016. I enjoyed it tremendously, and I'm very happy to be back virtually today and connect with a lot of good old friends and also meet new ones. So today I would focus on a problem we have been working on in the last few years related to modeling sequence of earthquakes and aseismic slip with high resolution fault zone physics, and with the ultimate goal of building a virtual earthquake machine. And I will explain in the next few slides why this might be relevant. This work is currently championed by two graduate students, Mohammed Abdelmajid and Mitcham Maya, but it was initiated by two alumni, Dr. Shauma, who's currently at ExxonMobil, and Dr. Sitari, who is now at Facebook. So let me see if I can, you see my next slide, right?
Yes.
So
yeah.
I usually put this slide in my first lecture in earthquake engineering, just to show the interdisciplinary nature of the earthquake problem. And of course, it's so vast and complex that we need to bring structure engineers, geotechnical engineers, seismologists, mechanicists, material scientists, and physicists to really understand the full spectrum of the problem. But what I would like to emphasize here is you see I plotted three figures that look identical on an XY plot here. But and those are meant to show the uncertainties, say in the response or a measured parameter at different foci, either the structure scale or the geotechnical layer scale or the source scale. And I plotted them like in a deceptive manner to show that they are all identical, but with a very important difference. The first one, when we look at the structure scale, I plot it on a linear scale. So X and Y are linear, and it's true we have uncertainties in the structural response, but we kind of have a good understanding of where these uncertainties are and we have a good control over it. But if we go to the geotechnical layer, especially when we focus on nonlinear site response, etc., actually the uncertainty will grow, and you may need to plot the scatter plots on a semi-log plot in order to make them tractable and get a sense of them. But then if you go to the source, it becomes even worse. Now you have to plot things on a log-log scale because just the range of uncertainty is tremendous. And you may think at the 21st century, we should have tools to observe and measure and detect earthquakes. And we definitely have been progressing in that respect. But even though we are still operating in data limited regimes, this is the map for all earthquakes that happened between 1900 and 2017 of a magnitude greater than or equal to 6. And as you can see here, for the most destructive earthquakes, the black dots, we may only have a handful of them, like 5. This is magnitude 9 or larger. If you go to magnitude 8, maybe you get 50, magnitude 7, you get 500, a few thousands of magnitude 6, but that's it, right? So for the bigger earthquakes that are most relevant to our infrastructure and impact on the socioeconomic structures of our societies, we really have very limited data. And this is why simulations are needed to bridge this gap. But as a modeler myself, there is a dilemma I have to deal with, like many in the audience here too. And that dilemma is, in order to understand the system, the modeler must first recreate the system on a computer, right? Or on a piece of paper. And in order to do this, he actually, or he or she, in order to recreate the system, they must have an understanding for the system. So it's like a chicken and an egg problem in some sense. Luckily, it's maybe easier in our case, although there are a lot of challenges. We probably are trained to start somewhere and then iterate. And when we look at the earthquake problem, it's natural to think, okay, we want to model fault zones. We look at fault traces, surrounding by damage zone, and we want to model that. The problem, of course, that even this is complex. They are, if we look at the fault zone, and we have been observing them only over maybe 100-year time scale. So what we are seeing in these fault zones is that definitely there are some persistent localized zones, which are recognized as fault surfaces or shear bands, and they exist within a dynamically evolving fault zone. So they are dynamically changing and evolving as a function of strain and time. And so you look at these, you find distributed and discrete damage features, and the system overall is what we call a non-equilibrium or far from equilibrium systems, that as a function of time, the properties are always evolving, but you could describe it in a statistical sense because it has some long-lived statistical properties, and we definitely have some nice statistical properties, scaling laws for earthquakes. And in that setting, the picture of an earthquake as a slip on a fault, the planar fault, becomes a little bit weak because you also have volumetric deformations coupled with deviatoric deformations. And these processes are depth dependent. And that's a challenge because we don't have still a technology that can allow us to accurately map what's happening, say 7 or 8 kilometers deep in the crust. So we are definitely tempted to make some approximations. And I'm quoting my friend and colleague, Yusuf Hashash. The idea is, of course, we are allowed to make approximations as engineers, but if we make arbitrary approximations, we may lose control over the error. So we may need to make approximation. We have to make them reasonable so that we have a bound on what to expect by simplifying things. In the earthquake problem, it's a little bit more challenging because the physics itself is not settled yet. So we really need to do the calculations first and then try to identify the first order effects and decide whether they matter or not, whatever we are neglecting. So the ingredients of this virtual earthquake machine, if I know people currently in the engineering community are interested in digital twins, it might be a difficult task to do a digital twin for the Earth since there's a lot of unknowns, but we would like to do something that mimic how the Earth operates. So in this virtual earthquake machine, we need to put faults and fault zones. We need to couple that with constitutive description that may be elastic or beyond elasticity, incorporating nonlinear effects, plasticity, and so on. And then we also need to track stresses and friction evolution. And people, of course, recognized this over the past 50 years when they attempted modeling earthquakes, but they were largely focusing on single rupture simulation. So let's simulate just a single event on a given fault. And we know that for these systems that has been evolving over a large period of time, if we just take a single event and simulate it, the results we are going to get are going to depend on the initial conditions that we assume for that event. But in the real system, these initial conditions have been evolving over thousands or millions, thousands or tens of thousands of years. So probably the prevailing condition currently are not known. So you cannot directly measure that. So that's a shortcoming of a single rupture simulation. Of course, you could think of maybe I can just assume different realizations of a stochastic processes as initial condition to start my simulations and run many of them. And that's a feasible approach, but we don't really know if ergodicity is maintained in that sense or not to allow for this. So the hope is we can put this in a cycle framework. We can let this evolve naturally. We start for some arbitrary initial condition, but then simulate the system for a long enough time so that these feedback loops come into one another, and through a sequence simulation framework, we could study actually how the system has come to the state it is right now. And people, starting from the pioneering work of Nadia Lapusta and Jim Rice in 2000, have been perfecting this with different approximations, but there have been some significant progress. It largely remained in the linear elastic regime with planar faults for almost perhaps 15 years after Nadia's work. But then people incrementally start adding more complexity, like viscoplasticity, viscoelasticity, non-planar faults, but with different levels of approximation. The most important ones are sometimes, in order to do these sequence simulations, you have to neglect inertia effect and replace it with some radiation damping or viscous effects to be able to track the calculation properly, or perhaps you cannot go to large scales and then you need to truncate your model arbitrarily, use something like a strip model, or put absorbing boundary conditions that are not perfect. So there have been some work, but it's with different levels of approximation. The good news is that there's a community now trying to work and push this boundary, the boundary of what we can do, because again, we cannot measure the system directly. So if we can improve our simulation capabilities, that would be wonderful for informing seismic hazard and understanding the underlying physics of the earthquake process. So from our side, the vision is we would like to go to high resolution. We don't want to compromise inertia effects because they are important during the earthquake phase. We would like to enable nonlinear bulk behavior. We would like to include multiple faults, because that's what happens when we look at fault zones, they incorporate multiple faults. And we'd also eventually like to allow these fault networks to evolve so that it's responding to the large scale stresses and small scale perturbation. So it's a network, so this network topology can change as a function of time. And as you would expect, there is no free lunch. So if that was an easy problem, then it could have been solved now. And the main challenge here is that there's a huge range of time scales and spatial scales that we need to deal with when we try to simulate processes relevant to earthquakes. And it ranges temporally, maybe you need to go from milliseconds to years, and spatially, you need to go from a process zone size, which could be millimeters to centimeters to kilometers in order to simulate that properly. So I will have my own share of approximations and focus primarily on a subset of problems that we think are important, but it's still a subset of a problem. And these problems that I'm going to focus on are where the complexities, structural complexities in the fault zone are relatively local and limited in space. And if I show you, like as I showed to you pictures from schematics of fault zone, or the one that you are seeing here in panel A, what we usually see is that there's a fault surface that's complex, can have splays and branches that looks like as it is quasi one dimension. So the linear, the extent, the length of the fault is much longer than the extent over which the damage is distributed in the transverse direction. And from real measurements, we would estimate this width to be perhaps 1 to 2% of the length of the fault. So in that case, we are dealing with a very interesting problem. We have nonlinearities that are scale large enough to affect the crack tip and control the energy flow to the crack tip as it propagates on the main surface. But in the meantime, they are limited compared to the other major dimensions of the problem. So you cannot just lump it on the fault surface as an effective friction or traction separation law, but you also cannot neglect it because it's large enough to interact with the energy flow on the crack tip. So for that purpose, we came up with a twist on an old idea, and that old idea come as follows. And I really vividly remember that in my last talk here in 2016, that was just a very preliminary idea. So now it has come a long way, and we are happy to push it further. And the main idea is, of course, if you want to model nonlinearities, finite element is the king. And so you could discretize the whole bulk using a finite element simulation or one of its variants, whether continuous Galerkin or discontinuous Galerkin. And the way we will do it is that, of course, we cannot simulate the full space or the full Earth. So we add usually boundaries far enough from the fault that you would like to study. And these boundaries are absorbing boundary conditions in the case of a dynamic event. And the hope is if they are put far enough, even if they are imperfect, then the reflections from them will not affect the dynamics on the fault. And in the static sense, you also still, because static fields extend to infinite distances, you also need to take these boundaries far enough so that the boundaries that you impose will not affect the static deformation on your crack. So that's the dominant method to do this. What we came up with is similar to what people have tried to do in coupling boundary integral or boundary element and finite element. We mentioned, since we are mainly focusing on this class of problems where we have heterogeneities or nonlinearities close to the fault surface, then let's isolate the region of interest in a kind of a virtual boundary here. These boundaries are just introduced, the dashed dotted blue lines are introduced as computational boundaries. These are virtual boundaries, they are not real material boundaries. But the interesting thing now is that we have a much smaller domain that we can discretize using whatever favorite volume-based method we would like to use. But the exterior half spaces are still important because they act as the energy reservoir that will drive this virtual strip. So the exterior half spaces here are being simulated using a spectral boundary integral formulation. And it's a boundary integral, but we discretize the spatial kernels in the Fourier domain, taking advantage from the fact that convolutions in space becomes multiplications in the Fourier transformation, and that in the Fourier space, and that accelerates the simulation significance. So the idea is you discretize the interior of that strip, but you have to communicate tractions and displacement to your spectral boundary integral. And by imposing this continuity on traction and displacement, you have the effect of the exterior half space, but at a much lower computational cost. Temporally, we came up with a scheme that allows us to take advantage of the vast range of slip rates that we would observe for that system. In the interseismic period, when things becomes quiet, inertia effects are there, but they are negligible. So we can actually use a quasi-dynamic approximation to solve that problem. And the quasi-dynamic approximation is mainly a series of static equilibrium problems that you solve driven by the tectonic loading rate. So at each step, you solve a static problem because you neglect inertia effects. And by doing this, by solving this quasi-dynamic problem, we can use or leverage adaptive time stepping schemes that can allow us to take time steps of the order of days, months, or even years, depending on how fast things are moving. On the other hand, as you approach the dynamic instability and when the system accelerates and inertia effects are no longer negligible, you could turn on inertia and solve the fully dynamic problem accounting for the inertia effect. And then, of course, we have to introduce a switch threshold to allow us to smoothly transition from this regime where inertia is not important to the regime that inertia are important. And I wouldn't go into the full details of the numerical scheme here. I would love to talk a bit more about the physics that we explore with it, but there's a series of papers that we have published, and I'm including them here, that outlines the method and validated and look at its computational efficiency, including this latest paper with my colleague David Kamer at ETH, where we actually extended the method to 3-dimension and showed that the cost of adding this spectral boundary integral layer is equivalent to adding just one finite element layer. So it's a very efficient scheme in that sense. So let me, perhaps in the next 20 to 25 minutes, I will just show you a few examples of application of this method. The first application was actually to test whether it's worth it. It's worth it to just focus on these small scale features in the fault zones and explicitly simulate them, or what we have been doing before, using some sort of a coarse graining to enable large scale simulation would be efficient. So the first problem I will show you is actually a full space with a fault in the middle. And this fault has an echelon of branches associated with it. And we do see this kind of geometry, maybe not perfectly parallel like this, but this fault branches, an array of fault branches associated with a main slip surface is abundant in nature. And we will make the specific requirement to test our hypothesis that these fault branches are small. And small here is measured relative to this elastofrictional length scale that governs the process zone size or the instability length scale in these frictional system. We are using a slip weakening friction here just for illustration purposes, where the friction at a point has a static value, static strength. Once the stress reaches that static value, the frictional resistance would drop to a residual dynamic value and then remain constant, and that drop happens over some characteristic slip distance. So we wanted to do these branches to be as short perhaps as this elastofrictional length scale, so that the slip contribution on these branches, if they get excited and moved, then this slip would be small or negligible compared to the main fault. And that was actually the motivation of neglecting many of the complexities in the fault zone, is that they appear dormant or appear small enough to actually to contribute to the measured slip or the moment released during the earthquake. So what we are going to do here is that we are going to nucleate a rupture on the main fault and let it propagate through the system and see how the existence of these branches, which are short again, affect the dynamics of the crack propagation on the main surface. And here's what we actually got. So one thing is, first of all, we get a significant change in the acceleration spectral amplitude. If we put a seismometer, say, on the edge of our virtual strip and measure how the spectrum, the Fourier transformation of this acceleration measured by the seismometer compared to the case where we don't have these kinds of branches, we observe that the spectrum is flat between 1 and 20 hertz. And that is something that engineering seismologists would usually observe in the near field. And then we get a spectral fall off for the high frequency, but the high frequency are definitely greater than the high frequencies that we observe in a homogeneous medium with none of these branches exist. So this is a mechanism for generation of high frequencies and producing the spectrum that we actually observe in nature. Another effect, for example, that would not happen if we don't have branches, if we look at the normal stress or the shear stress after the event is over, then these branches, the slip on these branches would actually introduce strong stress fluctuations on the main fault that will not be present if you have homogeneous systems. So this is another effect that emerges from these small scale features. And it even goes further. I will show a movie here that they may lead, depending on their orientation, and although they are small, but they may lead to qualitative change in the rupture behavior. So what you are going to see here is a plane view, looking at the fault from the top, and you are observing the velocity profile as the rupture is propagating. So let me run the movie. So the rupture is started, it propagates to the left and the right, and the tip propagating to the right will interact with the small branches. The tip propagating to the left will not feel these branches. And if I continue here, you would see that the one propagating to the right is actually producing these coherent wave phases that propagate for a long distance away from the fault. This is coming from the interference of the wave pattern that are generated due to slip on these small branches. And if I let it go further, you would see an interesting phenomena here. Actually, the rupture that is propagating into the right has transitioned into a super shear rupture, a phenomena that we don't see it much in Earth, but it happens. It's similar to an airplane exceeding the sound barrier in the air and producing a Mach cone. So if the rupture tip accelerated and exceeded the shear wave speed, you start seeing this Mach cone. On the left, where there are no branches, the rupture tip is propagating coherently. It produces high frequency, but only limited to the rupture tip. And you see the normal loops that are characteristic of a sub-Rayleigh rupture. So it's not only some small changes in heterogeneities or high frequency generation, but you get a significant qualitative difference in the behavior of your rupture. And of course, that is definite, that these were interesting results, but it definitely speaks to the shortcoming that I highlighted in the beginning. These are single rupture simulations, and depending on the initial conditions of stresses, friction, geometry, the results will vary. So we wanted to move beyond that and start trying the cycle framework. And our first application is in engaging this bulk is to try to look at the evolution of earthquakes and aseismic slip when you allow the bulk to become viscoplastic. And again, the advantage of our method is we can focus on a small region surrounding the fault, discretize it with high resolution, so we can access physics that may not be accessible if we cannot get to that resolution. And then we can run the system for a long period of time in a computationally efficient way. And the plasticity here, I'm showing it in a mode 3 setting. So it's an anti-plane rupture. And the plasticity formulation we are using are basically von Mises here, but with a pressure dependence in the yield stress. And the viscoplasticity approximation, as you know, mainly says that beyond a certain threshold, the excess, which is the yield stress, the excess stress in your system would be carried by a viscous damper, and then it relaxes to the rate-independent yield stress or rate-independent limit over a time scale that's related to the viscosity that you put into the system, as well as the elastic modulus of the bulk here. So when you do this, we start getting output like this. Here is, for example, a slip rate over time. And that is basically, we report at each time, what's the maximum slip rate that's happening on the fault. So when things are quiet, you could see that the maximum slip rate is about 1 nanometer per second. And whenever you see this kind of a spike, this spike represents high slip rates of the order of maybe 1 to 10 meters per second. And that is during the seismic slip phase. So when we generated this, we got a time history for the peak slip rate that looks like this. Every time we have a spike, that would indicate that there's an earthquake happening. And that was not very different from the from the sequence of events we are getting from the elastic case, except when we start zooming in on one of these spikes that appear as just one spike. When we do that, we recognize that there is a considerable amount of complexity in this spike. So if I zoom, for example, on this red, with the red rectangle, dashed rectangle here, and start looking at what is happening, in panel D, you would see that what appeared as one spike over the range of years now is actually multiple spikes separated by days or hours. So you have a swarm of events. You have multiple events happening during that period. And then if you even kind of looked at further, took for example, this orange rectangle here, you find that you have 2 peaks of slip separated by minutes. And if you zoom further, you could find things separated by seconds. So you start getting this sequence of events of different size of magnitudes during that period, foreshocks and aftershocks emerging naturally because of the existence of this coupling with the bulk and the viscoplastic effect. In an elastic simulation with a homogeneous fault, you cannot get this. You only get these large periodic events. And that is, here's the manifestation of this. On what you see in this plot are basically contours for the slip rate on the fault. So it's a space-time plot, the horizontal axis or the distance along the fault. So each point on the fault has a location on this horizontal axis, and on the vertical axis is simulation time step. And what we are basically doing is that at each simulation time step, we are plotting the slip rate profile, how fast the 2 sides of the fault are moving relative to one another, and we are stacking this together. So in an elastic case, you basically get periodic events that are repeated on a regular pattern, simple periodic events. The system settles into this simple limit cycle. Whereas when you turn on the coupling with the elastoplasticity or viscoplasticity, you start seeing a much more complexity in space and time. You start getting events that nucleate at different places. Like, for example, the red dots here signals the site where the event started. And you can see that the extent of the different events are also relatively irregular, right? So you get events of different sizes. Eventually, you can get a fault spanning event, but you end up with multiple partial ruptures and events of different magnitudes. And I will go quickly over this, but this is actually, this behavior is a function of the system properties. And that gives us a confidence that this is not just a numerical artifact. It depends on the yield strength of the domain, as well as the competition between the different time scales that we are currently engaging. So on one hand, we have a time scale related to the stress relaxation in the viscoplastic bulk, and that is what is eta over 2 mu is measuring. And we have another time scale. Remember this process zone R that I showed previously. There's another time scale related to the stress transfer or the stress changes over the process zone size, and that is roughly given by the length of the process zone, where the stress goes from a peak to a minimum value divided by the rupture speed that we can approximate as the shear wave speed. So the ratio as this number, dimensionless ratio changes, the complexity of the system changes. If the viscous relaxation time scale is too long compared to the time scale that the stresses are redistributed due to the breakdown processes, then you get periodic behavior similar to the elastic case. If you now introduce this redistribution of stresses due to the viscous relaxation on a time scale comparable or shorter than the frictional time scale, you start now moving towards this and having more complexity. Similarly, if you lower the yield stress, you allow the accumulation of more plasticity, so you will get more complexity. But now if you raise the yield stress, you will get less and less complexity and go to simple periodic behavior. And this complexity that I showed here are also like in the bulk. When you look at how this plastic strain is distributed, it's quite heterogeneous. On this column here, we look at the total accumulated plastic strain, and on the right column, the plastic strain accumulation within each cluster of events. So within each events separately, and it's pretty heterogeneous, analogous to the messy structure of fault zone that we would observe. But interestingly enough, you could compare the extent of this plastic deformation to the length of the fault. The length of the fault of the order of hundreds of meters, a couple of kilometers here, but the extent of this plastic strain is only perhaps 10 meters or less. So it's narrow, it's small extension in the transverse direction, but it has a significant effect on the rupture dynamics and the sequence of earthquakes. And typically you would like to think about this in terms of a global energy balance. Perhaps plasticity dissipates a lot of energy that interferes now with the other energy sinks in the domain, and hence alter the behavior. But that didn't turn out to be the case. We actually tracked the plastic work as well as compared to other energy dissipations in the simulation, like the frictional work. And if you compare here with different viscosity, you compare the scale of the two plots, there is mainly, it says that the plastic work is perhaps 1% or maybe a few percent of the total dissipation, which is pretty remarkable. So it's a small number or a small fraction of the energy budget is being dissipated in plastic work. So probably this is not the right way to try to think about what's happening here, why plasticity is altering the behavior that much. What is the key phenomena is that the plasticity effect is amplified through its feedback on the stress. We introduce another threshold in the system now by introducing a yield stress. And now I'm just looking at it in the limit of a rate independent phenomena or a rate independent plasticity, so that we can have a well-defined yield stress to discuss. If you have just a purely elastic system, then you can concentrate the stress ahead of the crack tip. And there's actually, you can concentrate the stress as much as you can, the friction would respond to it. But by introducing this yielding, then you reduce the ability of the crack tip to concentrate the stress ahead of it. And thus, by depriving the crack tip from this amazing characteristic that is associated with linear elastic fracture mechanics, that you can concentrate, the stress concentration increases as the crack length increases. By depriving the crack from the ability to concentrate the stress or lower it, you are actually helping the crack to self-arrest. So eventually, in some situation, this reduction in the stress concentration will help the crack to stop and extinguish itself. And I will show just a movie here very quickly. in the bottom panel, Shomon plotted the stress, and on the horizontal axis, this is the distance along the fault. And you could see different values of strength. I would like you to think about the yield strength and how the sigma 2,3, which is the stress component that's associated with that, would evolve. And on the top panel, this is the slip rate. So let me run the system here. So initially, as the aseismic patches creep, it starts concentrating the stress. So the fault strength is what is the friction is currently measured on the fault. And so as the creep goes into the central part of the fault, the stress is being concentrated. Eventually, it reaches the yield surface. And once it reaches the yield, you start accumulating some plasticity, even when the slip rate is aseismic. And then I will let it run again. Of course, this is a viscoplastic simulation, so you could actually exceed the yield by how much viscosity we are allowing. So now I'm accelerating it. I would like you to see what happens at this point, where the stresses now in the plastic zone are clamped at the yield stress. So you could see this shoulder here. This is a pinning effect that plasticity introduces to the crack. And you would see that in the slip rate, there is actually a reduction in the slip rate. And if the rupture wants to nucleate next, it has to nucleate beyond the plastic zone. So I will switch gear in the next few minutes just to show you other examples where we can apply this. Okay, so you are still with me, good. Other examples that we can apply the phenomena with. So of course, we know that there are multiple faults in the fault zone. So we simulate now a step over, where we have two faults communicating with one another, but they are not in front of each other. There is a gap separating them. And if we turn on this machinery, we can generate earthquakes on both faults and study how they interact with one another. Would a rupture, for example, jump from one fault to the other? How is the stress effects due to slip on one fault affects the stresses on the other fault, and so on. And again, we can generate these slip rate as a function of time, but now we have two faults, so we can put them next to each other and study the delay in the seismicity between the two faults. And what we would see here, for example, again, the similar plots, but now because of the existence of these two faults, we get events on two faults. There are some delay in time between the events on two faults, but more interestingly is that you start even getting partial rupture here without plasticity. So now, because of the stress shadow effects and the stress heterogeneities enhanced by the communication between the slip over the two faults, the stresses are no longer homogeneous on the fault surface and they become heterogeneous, and that allows generation of these partial ruptures. If we move it even further and now add plasticity to it too, we observe more interesting things. First, we can track the evolution of the damage and plastic strain that is accumulating between the two faults, and we definitely observe this region between the two faults that are significantly damaged with successive deformation and rupture propagation. And you can also see these two arms here that are characteristics of the interaction between two faults approaching each other. And if I look at the same plots of slip rate as a function of time, but at different levels of viscosity, we can measure how plasticity alter the delay time between events on the different faults. So if you have a small plasticity, either the medium is stronger or the viscosity is large, then there would be hours or days of delay between the event on one fault and the event on the other one. So it's only just a static stress communication. But if you increase plasticity, So you produce more plastic deformation in the medium. Plasticity actually, and there's a very fundamental explanation for this, would facilitate faster communication between the two folds, and perhaps either one fold can jump to the other in the same event, or the difference in timing between an event observed in one fold and the other becomes shorter and shorter. So here becomes it's minute instead of days or years. And finally, I will stop here. This is just a teasing slide. We have been collaborating with Professor Jinhyu Xu in KAIST here and developing a phase field model for fault nucleation and growth that can actually converge to rate and state friction. It builds on the idea of cohesive phase field, and there are so many limitations, of course, for phase field as well as many interesting and powerful phenomena that can be discussed with that. But at least for this application, we have tried to validate it against simulations of sharp faults with rate and state friction. And the idea here is not only allow the evolution of the bulk, but also allow the evolution of the fault trajectory itself. So for example, here's a simulation with a short fault that we trigger a rupture on it, and then as the rupture reaches the ends of the short fault, starts accumulating damage, but it also starts extending on its own. So you see the sharp localization here. This is signifying the extension of the fault at different time steps, and these bulbs at the ends represents the damage in the domain. And if we simulate, if we sprinkle some heterogeneity in the domain, we start generating these kinds of lenses and bands that to some extent mimic what is the structure that's observed in natural fault zone. So to conclude, I think what we are trying to do, again, as a modeler, we need to build the puzzle and then we put it together. And I showed just some parts of the puzzle today, but there are many other important ingredients like shear heating and fluids and so on. So we try to put these pieces of the puzzle together, but the emphasis and the critical piece that we would like to go after is this evolution or feedback. We want to do this in an evolutionary framework that we allow feedback from different mechanisms. But after doing the hard work, and this is something I would like to share with my friends here so that the expectations are clear, is after doing the hard work to learn what's relevant and what's less important, we will actually need to simplify. So we are doing all of this not for the sake of making our models more and more complex, but basically to identify what is the first order dynamics so that we can hopefully be able to homogenize if possible, and or develop reduced order model that can describe this complexity. So this is a long-term goal, but we are trying to put the foundation for it now. So just to conclude here, I believe this is an exciting time for earthquake science because we have the tools, computational tools, the computational resources that would allow us to go beyond what has been possible in the past 50 years. An example is the hybrid scheme that I introduced today, and these high resolution, but there are other many fantastic examples from other groups in the field as well. These high resolution models will eventually help develop and inform reduced order models. And specifically for the cases I introduced today, I would like to emphasize that off-fault plasticity may act as a self-limiting mechanism, leading to emergence of space-time earthquake complexity. And this question of earthquake complexity is still a very active one. The contribution of off-fault plasticity to the total energy budget is small, but that is not why it is leading to this complex behavior. It's the feedback on the stress and the stress redistribution is what is amplifying the impact of off-fault plasticity on earthquake physics. And then finally, I just show you a glimpse that off-fault plasticity may facilitate rupture jumping in fault step overs compared to the elastic case. So I would like to thank Emmanuel and all of you again for listening, and I would be happy to take any questions.
Thank you very much, Ahmed, and please join me to congratulate you for a very nice, very interesting lecture. Sorry.
Thank you.
Okay, so the floor is open to questions, so to speak. It's a virtual floor. Somebody wants to start? So maybe I can start to ask questions. So I was thinking in terms of your problem of example number 2, where you showed you have this kind of a phase diagram.
Yes.
You have this ratio of time scales, then you have this scaled yield strength, and you show that change of complexity, and then you show that you have this the very kind of simple periodic.
Yes.
In the case it's elastic or in one part of the diagram, and then you show increasing complexity. I'm just wondering, is that do you still observe limit cycle, but more complex limit cycle?
Yeah, that is a fantastic question, because it's also a function of the mode that we are studying. So in this problem, eventually we don't see a limit cycle when the system transitions into complexity. It seems like the complexity is persistent. There might be some aperiodicity, so you could perhaps identify some clusters and repeated on aperiodic time, but it's not limit cycles in the strict sense. In other applications that I haven't shown here, for example, if we switch to mode 2 ruptures instead of mode 3, then we engage normally stress changes, because if you have a shear rupture, then it also changes the normal stress in the bulk as it propagates. And what we observe in that case is that we get another feedback through this normal stress, which also changes the yield surface. And surprisingly, eventually, the system could start complex and then settle into a limit cycle. And what geophysicists will call this, it's called fault maturation. So younger faults that are still spinning up the ruptures usually show complex event sequences, but as they start accumulating larger and larger amount of slip, they seem to settle down into a more characteristic cycle. So there are definitely cases that, as you are suggesting, where we can transition into a limit cycle later in the dynamics.
Okay, thank you. Is a question from Nikita?
Yes, hello, Professor Elbanna. Thank you very much for your presentation. So I'm wondering about these sequences during the spikes. So it's very similar to aftershocks and foreshocks. So I wonder about in seismology, there are relatively well-known self-similarity of these parameters. Let's say Amori-Utsu law, when it's decay of the aftershocks. So is it possible to match these values from seismology in your model? And is it possible? And if at this moment not, how we can modify it or something? Thank you.
This is an excellent question, Nikita. And these are target validation problems. It just needs, like we do observe a glimpse of that, like you could see already that there is a range of time scales that are engaged in these kinds of foreshocks and aftershocks. It's just the system size here is relatively limited. It's still large, but relatively limited to produce the range that is observed in reality. So by extending, say, the size of the fault or adding a few extra faults, as I showed later, we could start matching these scaling laws. But questions related, say, to Gothenburg-Richter relations as well as Omori's laws are very relevant in that context. And I think we are heading towards that direction to explain them.
Okay, yeah, thank you very much.
Thank you.
Hi, may I have a question?
Hi, yeah.
Hi, very nice talk. I just wonder that you clearly show that the local features are important of this fault behavior. So do you have any insights on how the material randomness in the fault will affect the behavior?
Yes, so this is, again, I anticipated that question, and I still would love to collaborate with an expert in that respect, right? But I think it does affect it strongly, not in the sense that it will broke what we are observing, but probably it would enrich it. And I showed a case, for example, in the phase field simulations that I show it here, and I went over it very quickly. But this simulation, basically, in order to generate these kinds of fingers and lenses, we need to assume a distribution of fracture energy in the system. So the critical fracture energy that goes into the phase field formulation has to be according to like Gaussian distribution or something like that, of course. But I think it's important to incorporate the heterogeneities in two, because it has two implications. One, it would stabilize some numerical artifacts related to localization, etc. And then it would actually enrich the patterns that we are going to observe. So it's a very important point.
Okay, thanks.
Other questions? I'm fascinated by this dual aspect of plasticity. You know, the dissipation side and then the limit stress side, and as you show, it is the limiting stress which is affecting the system and not the dissipation.
Yeah, we were also surprised to see this, and I think perhaps, although this is kind of a hand-waving argument, is so in statistical physics, people study these nonlinear system with thresholds, and usually once you introduce threshold coupled with dissipation, it starts like this was the origin of self-organized criticality and things like that. So once we have these thresholds in the system or different time scales competing with one another, we start seeing that this phenomenon, these complex phenomena, even if dissipation is small, because at the end of the day, maybe dissipation is small compared to the other energies in the system, but what matters in crack propagation, what's happening at the process zone scale. So if you manipulate what's happening at the process zone, it may not matter much what is the big energetics are. Maybe the energetics overall would start changing some aspects of the slip distribution, etc. But it's really what is happening at the process zone that is important. And maybe when we compare the breakdown energy to the plasticity, maybe they become comparable. But if I compare plastic dissipation to the total energy of the system or all the frictional dissipation that happens, etc., that's where it becomes negligible. So it's a small fraction of the total energy that's perhaps what we are confident about, but it might be actually comparable to the changes in the energy or the energy flux that is going to the crack tip.
I see. Any other question from the audience? No? Well, again, let me thank you again for a very, very nice lecture. So a lot of food for thought. No?
I'm very grateful for the invitation, Emmanuel, and I'm very grateful for the audience also to attend. And it was, I was very much looking forward to it.
And I hope to see you in real, in 3D.
I look forward to, I hope if you are going to EMI or if others are, then I would look forward to catching up with them too.
Right. Okay, thank you again, Ahmed.
Thank
you, Ahmed. Thank you.
Thanks, Stefano. Thanks, everyone. Thank you.
Thank you, Ahmed.
Bye. Thanks a lot.
Thank you.